So following previous speakers, let me start with 2 words about David Gross. What can I say? I met, I guess, David like 30 years ago, about 30 years ago at Landau Institute when he was visiting Moscow. And, sorry? You can't hear me? Oh, is it on? Oh, can you hear me?
Is it on?
It's on. It's on.
Yeah, it's on. So speak louder.
Yeah. So 30 years ago, it was a very exciting time of string theory, and I vividly remember David sitting with his feet on the desk, very intimidating, and asking various sorts of questions. For example, okay, you know, first few terms in effective action, so what? At the same time, he was writing papers about exactly that same subject. But it was quite inspiring, and reading David's papers was always very inspiring, apart from papers of early 70s, about loop correction and dual models, which I failed to understand when I was young, and still probably. Anyway, so the subject will be closely related to the previous talk, but I will be in 4 dimensions and higher. So massless high spins, not in 3 dimensions, but 4 and higher. And the talk will be very elementary so compared to the previous one, but it will also be restricted mostly to free high spin fields. So it's based on these 2 papers. So any kind of new result will be from these 2 papers. But the kind of general motivation is to learn about quantum corrections and high spin theories, but also to learn about high spin theories, because we don't really understand the theory in ADS should exist because of ADS CFT, but there is certainly a bigger picture. And so the main motivation is checks of ADS CFT, and in fact, one particular question is to see kind of hidden simplicity of this high spin theory, Vasiliev type theory. So essentially it should have no 1 over n corrections, at least in one way of formulating this theory. No quantum corrections. So another interesting question, which I will not really address, but this is part of the motivation, is to try to understand how high spin symmetry is broken if you change boundary conditions for a scalar field, because that theory should be dual to interacting fixed point. But that's kind of future goal. So massless high spins in flat ADS. I'll start with very general introduction, trying to kind of draw a bigger picture, possibly. So there is an old, it's a very old story about whether you can consider massless high spins in flat 4 dimensions. For example, there is a free action, but whether there is interacting theory, there are various no-go theorems, and even relatively recently there were discussions based on S-matrix arguments, BSFW arguments type. And there are various constraints, but in fact such theory may exist. It may be very unusual and singular in some ways, and very non-local effectively. But what we know about how it should look like, it essentially should contain infinite tower of high spins. The simplest version is 1 spin enters just once, and its 3 derivative coupling should be a very special form. So that essentially follows from starting, say, from light cone gauge and closing the Poincare algebra. So that's some references. Essentially, the conclusion is that this 3-point vertex is essentially unique, but it contains non-minimal coupling, non-minimal interaction. So, for example, spin 2 interacting with other high spins will have high derivative couplings, not minimal, not through stress tensor. So that's the kind of 3-point function. And interestingly enough, that same argument about closure of Poincare and light term gauge fixes the coefficients in front of this 3-point function, and these coefficients happen to be the same. It was a paper like last couple of days ago. The same coefficients appear in ADS high-spin theory. So the 3-point function between 3 spins is actually fixed, and the theory contains just 2 couplings, should contain. So one is like the coupling which one in front of the action, which counts the number of fields in perturbative expansion. And there is a dimensional coupling, like a scale L, and so that's roughly what one should get if such theory exists. But the quartic coupling is not constructed yet in full generality, so it's still an open question. But what is clear that the number of derivatives should grow with number of fields. So this theory effectively is non-local. It's very kind of unusual type. And there is a difference compared to ADS theory, which I'll emphasize once I get there. But why this theory may be of interest? One point is that it does contain very large symmetry related to gauge symmetries, a global part of gauge symmetries of these high spin fields. So a priori that has nothing to do with string theory, but it's possibly this massless theory in flat space can be understood as certain limit of Vasiliev theory in ADS. For example, as I mentioned, cubic couplings are the same. And basically what you need to do is in ADS you have more lower derivatives in the couplings, and you need to drop them in this kind of singular limit, and then you should end up with something like that. There were also suggestions that you can get that theory by taking certain truncation of singular alpha prime limit of string theory, for example, just restricting the leading Regge trajectory, but it's not completely clear whether this limit can be actually performed in any reasonable way. But still, it's interesting possibility that this theory actually exists. But my point will be that this theory may look very strange and unusual, but it may actually be much simpler than it looks like. So it may have some hidden simplicity in it. Basically, same will apply to ADS case. So for example, it will have 0 number of degrees of freedom in certain precise sense in which I'll try to explain. So what about ADS? So here there is already second derivative coupling. Second derivatives appear in the coupling. So there's no go theorem, and it can contain minimal interactions. It will have a relation to this ADS CFT duality. But what we know here, we know the cubic coupling from some late 80s. Then there is a formulation of Vasiliev, which is kind of closed equations of motion, but they contain infinite number of various auxiliary fields in addition to physical Fronzel fields. So how to eliminate these auxiliary fields is unclear. How to construct the action to all orders is unclear. But now there is a good emerging understanding how to do this, trying to match to ADS CFT. There is a cubic quartic couplings, which some of them are fixed. But essentially, this theory has also 2 parameters. The coupling, like what appears together with h bar, or 1 over n in ADS, and the scale, which is already ADS radius. And it's due to free CFTs in flat space or on a sphere. So essentially, you can consider scale as a spin, as free scale is in any dimension, 4 vectors in 4 dimensions, 2 forms in 6, etc. So conformal free theories in 1 dimension higher will be due to that theory. And so this similar theories, so here you need to take fields in fundamental representation, so that's what is called vectorial ADS CFT, simplest example. But there should be similar theories which should be related to zero tension limit of strings in ADS, which should be better defined than in flat space, which is still not really much known about this. They will be due to not just Vasiliev type theory, but to collection of Regge trajectories, which will be massless plus massive Regge trajectories. So some basic example is CFT, like Maxwell theory, where you have a joint n = 4 Maxwell theory with fields in a joint representation. So no interaction, but large n limit should be due to theory containing all sorts of operators which will be due to massless and massive fields. So another closely related theory is the one with broken high spin symmetry, which should be due to interacting fixed point say in 3 dimensions, this Wilson-Fisher point, which was discussed by Klibanov and Polyakov. So now there is another another high-spin theory, which is non-unitary, but still very closely related to massless high-spins in ADS, which I'll be discussing. And that's what is called conformal high-spin theory. In some sense, it can be viewed as some induced theory at the boundary. And it has maximal, why it's interesting, it has maximal possible symmetry, which one could imagine kind of high-spin generalization of conformal symmetry, where you have derivative gauge symmetry plus you subtracted traces. So it's like wild gravity having both diffeomorphisms and wild symmetry. So here there's only one coupling. It's conformal theory. So there's coupling in front of the action. There is no scale. So the vertices, derivatives in the vertices are all fixed. They fixed just by dimensions of this field HS, which has dimension 2 minus s in 4 dimensions. So this theory has high derivative kinetic terms, so it's perturbatively non-unitary, like wild gravity, for example. So spin 1 here will be maximal, but spin 2 will be kind of wild gravity expanded near flat space. But it's of interest because it's closely related to this massless high-spin theory in ADS, and there are certain features which will be similar in quantum theory. One very mysterious thing about this theory, it looks like it will be UV finite, properly formulated, and there will be no conformal anomaly. So this theory may be consistent despite having this analog of wild symmetry and having no supersymmetry. So essentially what happens, just kind of going ahead, the big symmetry means you have lots of kind of Gauss determinants which play the role of fermions. They cancel some of the physical contributions. So the aims will be essentially to better understand both ADS CFT and high-spin theories and their interrelation, and study these these theories with infinite towers of spins. How they should be defined, that's the main issue. Namely, how you sum over spins, how you regularize this sum. And we don't have this guidance which we have in string theory, like we have worldsheet formulation, first quantized formulation. Here, unfortunately, it is not known what would be the analog of that. That's one of the open questions. Presumably, there is some particle theory behind Vasiliev theory, but that's not known. And that essentially a missing point, which requires deciding how you actually preserve the symmetries in quantizing the theory. So that part of motivation what I'm going to discuss, and let me just go straight to some kind of quick review of this vectorial ADS CFT. So essentially, suppose we have 3 complex scales in fundamental representation. We have conserved currents. We look at singlet sector of primaries, and these are dimensions. That's a familiar story. So the spectrum of these currents is the same as the spectrum of Vasiliev theory in ADS, and essentially this theory summarizes correlations of this singlet of these currents, JS. So there is a one coupling, which is 1 over square root of n. It's a free theory, so all correlations are simple, just determined by weak contractions. And then when 3-point functions, some of them are basically fixed by symmetry. And that was work by John Benyin. They compared them to 3-point functions which appear in Vasiliev theory, found matching. But what is going now, basically last year it was understood there are various subtleties in this relation between 3-point functions and vertices. In Vasiliev theory, still rules of the game are not completely clear. So essentially one needs to formulate Vasiliev theory. Extracting physical content from Vasiliev theory still remains an open question. But one thing is clear. So suppose we have we manage to get some action for Fronsdal fields from Vasiliev theory. So we get an action like something like that. There will be n in front of the action because 1 over square root of n is coupling, effective coupling on ADS side. There will be kinetic terms which correspond to massless high spins in ADS. There will be cubic interactions at quarter-kinetics, etc. And then quantum effective action. So that's a classical action. Quantum action will contain one loop correction which will have no n in it, 1 over n, 2 loop correction, etc. And that action should be related to generating functional conserved currents at the boundary, which are bilinears with certain derivatives in them. And the sources for these currents essentially will be these conformal high spins because sources are conserved and traces on shell, so these symmetries will emerge. But the basic point is that at the boundary, the generating function for the current, for the correlation functions of the currents, is given by simple formula, just n times log determinant. N comes from fundamental of these free scalars. And this is log determinant of these sources HS coupled to the operators appearing in bilinears in the current. So this has n dependence in front, while on the ADS side, you're supposed to take this theory, Vasiliev action, in exponent and do some path integral with boundary conditions, which you fix to be sources to be HS at the boundary. So you clearly get quantum corrections weighted by 1 over n, while there's n at the boundary, which is just classical contribution from that point of view, from the ADS point of view. So if you believe this matching, all quantum corrections in Vasiliev theory should be absent. So that sounds a bit strange, but one caveat is that that should be true at separated points if we believe in matching correlation functions. What happens at coinciding points depends on how we actually define the symmetries, and these are related to contact terms, etc. But at least with this definition of matching to ADS, that seems to be the conclusion. And so one motivation is to try to understand this matching and try to define in which sense this matching can work. So now we can go further. We can imagine matching of correlation functions and then summing them up and integrated correlators, and then we will be having matching of partition functions. So suppose we take CFT partition function on some non-trivial background, and that should match this ADS massless high-spin partition function in asymptotic ADS. So that will that's a kind of very strong extra assumption or conjecture, which depends again how we define how symmetries are realized on both ends and how these contact terms are defined. But again, if we believe in that, all quantum corrections in ADS should be trivial, so partition function should be 1 to all orders in coupling. So first, we need to see whether this is true even to leading order, to one loop order, whether the partition function is 1. So that's what I'm going to review. But let me start with flat space and go back to this massless high spins in flat space. So imagine we take just 3 massless high spins in flat space, and we sum up together scalar, vector, spin 2 massless fields. And all we know is basically that in 4 dimensions, each of these high spin fields have 2 degrees of freedom. So now imagine looking at this silly equation, which says that 1 degree of freedom of real scalar plus 2 degrees of freedom of vector, of graviton, etc. And you sum this infinity using zeta function. Then you get 0. So that sounds a bit wide zeta function. Sounds a bit naive, but surprisingly, that equation actually turns out to be the right thing with proper regularization of what we need to do. So just to start with, what is the partition function of the free spin S massless field in flat space or in a torus or finite temperature? So it's actually a ratio of determinants defined on transverse fields, and that's what gives you 2 degrees of freedom if you just cancel these boxes. And now imagine taking product of all these ratios. So you'll have a scalar, vector, spin 2 factors, and you see that if you naively cancel the physical spin 0 against the ghost part of spin 1, ghost spin 2 against physical spin 1, etc., you actually get 1. So that again is sounds a bit too good to be true, but of course it's ambiguous. It's an infinite product how you define why you cancel that way or another way. But if you imagine this is true, this reminds us some kind of topological theory, Chern-Simons theory, and it's in contrast to supersymmetry where there is a similar cancellation. That will actually work even at finite temperature because these are bosonic fields, so they have the same statistics. But again, this is ambiguous, and it depends how we define this sum. So the point will be that this sum should be defined in a certain way which is consistent with this statement, and that same story is true in ADS. So essentially that's what I was just saying, that if we look at degrees of freedom count, so each of these determinants is essentially degrees of freedom in power, box in power degrees of freedom, nu s. And nu s is just 2, and summing these, the sum to be 0, it's equivalent to that cancellation which I just discussed. So the zeta function regularization is equivalent, Riemann zeta function regularization is equivalent to canceling these factors in z in the way I described. And that, again, we know that zeta function appears in, say, computing vacuum energy in bosonic string. And that is consistent with certain symmetries in target space. So that's not the first case we see that, but so the indication is that that's the right prescription consistent with symmetries of this high-spin theory, though it's not kind of implicit here. And the same conclusion is true in d dimensions, but provided we use a very specific regularization, which is equivalent to zeta function, but it's easier to formulate it with a cutoff. So you just put an epsilon cutoff with particular shift of spin by half of d minus 4, and then you drop all singular terms and you get 0. And conjecture is that should probably be true also in interacting massless high-spin theory, because that should be true also in ADS. It would be consistent with ADS 50. So what happens if we consider high-spin theory in ADS of d dimensions? So the claim will be one-loop partition function is 1. But now it will be much less obvious why that happens. Essentially, one needs to write these determinants now in EDS, and there will be no immediate cancellation. So these determinants have certain mass terms consistent with symmetries. And so the ratio here will not be just boxes, but these covariant derivatives plus particular mass terms, which are different depending on spin. And there will be no cancellation if we just take a product. They will not cancel naively as it was in flat space. Instead, what one can do here is just to compute these determinants one by one using zeta function regularization, then sum over spins. Or one could first define these determinants using the zeta function and keep the cutoff or z argument of zeta function fixed. And then do sum over spins first and then take z to 0. And what turns out that you actually get 0. And you get partition function total be 1 using the zeta function regularization, provided you first sum over spins and then take z to 0. Now, if you do this the other way around, namely using zeta function first, then you need to sum over spins with particular prescription to get the same result. And that prescription is basically what I just have shown in flat space. It's the same exponential cutoff with particular shift and then take infinite part. So the bottom line is that if you first keep cutoff, do the sum, and that's equivalent to that prescription, and that should be consistent with symmetries of the theory. And then conjecture is that that should also be true beyond just free one-loop contribution, namely free kinetic terms, but also including interactions. How that happens is still remains to be seen whether this is true beyond one loop. An important point is that need not be true in contrast to flat space at finite temperature. So at finite temperature, you get non-trivial result, which is consistent with ADS CFT. It's counting characters. Essentially, this is what's called Flatter-Fronzel relation. Partition function, one particle partition function, curly Z. Its sum over spins give you non-trivial Q-dependent result, which is square of one particle partition function at the bound for a scalar. So now let me quickly run through how much time?
15 minutes.
Oh, very good. So conformal high-spin theory. Again, let me first discuss it unrelated to ADS CFT, but then I'll connect it. So essentially, you think of what is generalization of Maxwell theory, which has in 4 dimensions, which has conformal symmetry, it has gauge symmetry. While symmetry has both, expanded near flat space, it's certain spin 2 conformal theory. So we can go further. That would require having 2s derivatives in kinetic term. Reason being that if you demand projector which is traceless transverse, you have lots of 1 over boxes in this projector. So you need to cancel them to get local kinetic term. You need to put 2s derivatives. So this theory obviously is non-unitary, spin by spin at least, so it's not clear what is the asymptotic states, etc. But suppose we formally look at such theory. Remarkably, there is an action which provides all kinetic terms, at least in implicit form. It's essentially some induced type of action, which I'll show in next transparency. So in some sense, interpretation of this HS in context of ADS CFT is that they are shadows or sources for these conserved currents for free scalar. So that's why they kind of naturally appear both at the boundary, at least as auxiliary construct, and in the bulk. So what's about the action for this high-spin theory, for conformal high-spin theory? So suppose you take these scalars, you introduce these sources HS, and you integrate over scalars, you get determinant, which I have shown earlier, times n, or just without n, and then you just take log divergent or local part of this log determinant. If you just take local part, it will have the right nonlinear symmetries, which generalize this analog of Weil symmetry or conformal symmetry and diffeomorphism. So that kind of closed form for this action, in contrast to these massless high spins, we don't have similar formula. But it's not very explicit. In principle, I can work out what are cubic couplings and quartic couplings, etc. But here I just look at partition function, and again, we can start just with flat space. Essentially, it's a counting of degrees of freedom again. And again, there's no naive cancellation of determinants here, but the total number of degrees of freedom, which is this given by this formula, which is s times s plus 1, so 2 for spin 1, 6 for spin 2, etc. for wild gravity. And then with the same cutoff, which is here d minus 3 instead of d minus 4, because we are kind of in d dimension at the boundary, you get 0. So in that theory as well, you get 0 total number of degrees of freedom. So partition function, naive, flat space, trivial free theory partition function is 0. Now, moreover, conformal anomaly in this theory, A anomaly cancels. So if we consider this theory on an S4, one could see that its partition function S4 is 1. And that is actually consistent with what I mentioned earlier about partition function on massless high spins on ADS, because there is a remarkable relation between partition function of conformal high spin theory and massless high spin theory for each spin actually, with different boundary conditions. If you take plus and minus boundary conditions for massless high spin, you get that statement. So these partition functions that happen to be 1 when taken summed over product over spin. So the same should be true for this one. But that one can check explicitly just doing this computation of these determinants for conformal high spins. And what do you get for each determinant? Log z for each spin is essentially A anomaly coefficient times log divergence times radius plus finite part. And that's how this A anomaly looks like as a function of spin. So if you sum this over spin, and the finite part is transcendental, and there's also sort of constants, Gleicher constants, etc. But if you sum this over spin with that cutoff, dropping singular terms, you get 1. Both A anomaly sums to 0 and finite part sums to 0. So it's kind of non-trivial, but it's essentially related to that relation.
Just to be sure I understand, this is with the same boundary condition for all the spin.
Conformal theory is defined on S4. On ADS, you have it's true for both plus and minus. Each of them is 1. So each of these is not for every state.
So
Product of moreover, under certain natural condition, also C coefficient for this for conformal high spin theory. In general, for each spin, you have this relation with conformal anomaly. You have 2 coefficients, A and C. And C minus A, under certain conjecture, you can compute this on Ricci flat space, these determinants. And then you get that C minus A is given by this expression. And then if you sum it over S with the same prescription, you get also 0 for C minus A. So that means both A and C coefficients are 0, which is quite remarkable that it looks like non-trivial theory, but it has this conformal anomaly 0, so that means it's UV finite, at least that's all at 3 levels, so 1 loop low order in curved background. So let me now quickly run through some other computation, again to illustrate this relation between cutoff and preservation of symmetry, how we sum over spins and how we preserve the symmetry. As an illustration, a very simple computation of the following diagram. So suppose you have some scalars interacting with conformal high spin. So exchange by all tower of conformal high spins interacting with scalar through this conserved current. And this is some kind of analog of Veneziano amplitude and string theory. But here we exchange the tower of conformal high spins. So that's what we are going to do. So this is phi is a scalar, and Js is the conserved current for the scalar free, and Hs is a source. And for Hs, we add an action, which is essentially quadratic action for this conformal high spin. So it's a usual coupling, vector couples to conserved current, while graviton couples to stress tensor, etc. So you sum these up. So it's straightforward computation. Just the only difficulty is properly normalize this kinetic terms of conformal high spins and do this trivial computation. Propagators you need to, even that is simple because the currents are conserved on shell, so it propagates essentially delta functions. And what you get in T-channel, for example, amplitude looks like this. It looks a bit complicated, but let me just say what you get if you, for each spin, contribution of each spin, in terms of Mandelstam variables, looks like this. It's a Gegenbauer polynomial over ratio, s minus u, s plus u. There is a prefactor 1 over t in power d minus 4. This is purely, it's a scale invariant theory in any dimension. So this is just a proper dimensional factor in d not equal 4. In 4 dimensions, just Legendre polynomial, and there is no prefactor. And it depends on ratio of kinematic variables because it's a scale invariant theory. There's no dimensional coupling, massless theory. So if you sum this over spins, what do you get? You get certain function of the ratio. And this function is essentially this Gegenbauer polynomial with alpha d being this d minus 3 over 2, s plus alpha times c. You sum this over spins, but you need to decide how to sum over spins. So naively sum diverges, just like for these degrees of freedom count or all these partition functions. Sum over spins naively diverges, unless we first keep cutoff, do the sum over spins, and then take cutoff to 0. But in general, we don't have this other procedure explicit. So we devise a procedure of how we first compute, then sum over spins with a certain prescription. So the prescription is basically the same. You introduce a cutoff, which is exponential cutoff with particular power of spin. And what you end up with, say, let me just look at 4 dimensions. You end up with delta function of the argument being the regularized expression for this f. So again, the amplitude is just f up to prefactor, f of the ratio of s minus u, s plus u. And you get delta function of z minus 1, which is s minus u over s plus u. So what does that mean? So that's explicitly what we end up with, essentially. But the bottom line is this strange amplitude, which is scale invariant theory. G is dimensionless, so it's just delta function. It's essentially 0 if you look at kinematics, and everything should be real. There are no complex momenta, so you get 0 for this amplitude. So what does that mean? Sorry? It should be 0. The reason why it should be 0, there is an argument from conformal high-spin, global part of conformal gauge symmetry. It contains essentially what's called super translations, or hypertranslations. It's transformation of a scalar with not first derivative, but R derivatives. And that's part of this bigger gauge global symmetry, which is kind of global part of gauge symmetry. So that symmetry, there is an argument which I'm not going to explain, but it basically constrains this particular amplitude and fixes it to be delta functions up to prefactors. And then scale invariance fixes the prefactor, so the amplitude should actually be 0. And that's what we get with that particular regularization prescription. So that's essentially the message that in that particular example, we see the relation between symmetry and particular prescription for summing over spins. So I'll skip loops because here things get a bit hairy and unclear at the moment, but basically you can do various loop diagrams like this, and then again try to see whether there is a relation between prescription of how we sum over spins and what we should expect. So let me just conclude. So that story, loop story, is still not completely understood. So And for loop story, we need the vertices for high spin, so that's why it gets much more complicated. So conclusions, basically, we try to learn about both high spin theories and how to do quantum computation in them. And what I try to emphasize, it's important to understand this issue of, it's a theory with infinite number of particles. So string theory we're used to, we know how to do computation string theory. If you didn't know first quantized formulation, just given string field theory, I think we would be pretty much stuck, because you need to formulate all sorts of notions of locality, how interactions, and lots of ambiguities. So here we basically, in massless high spin theories, we don't have that luxury of knowing proper way of doing computation. So we need to invent, and at the same time, this is a much simpler theory. It just has one tower of this high spin field. And there's a huge symmetry, and remarkably, it might be that these theories are much simpler than it looked like. So as I try to emphasize, they have 0 degrees of freedom, total number of degrees of freedom. Partition functions are 1 in flat space, even at finite temperature for massless high spins in flat space, but in ADS it's what it should be. It's non-trivial function of beta. Now, in some sense, this massless high spin theory, if it exists, it may be analog of what may be called integrable theory in higher dimensions. Maybe it's just free, but it looks like cubic interaction at least is non-trivial. So in which sense? Because what basically Weinberg's theorem, Weinberg's argument gives us an indication there should be higher conserved charges, and indeed this theory should have higher conserved charges. So it might be there is some notion of what, in that sense, why it's simple, because it's some kind of analog of integrable theory. And presumably the same should be true also for Vasiliev theory. It's due to free theory, after all. So in some sense it must be simple. We just look at it in a way which it looks very complicated. At least we don't even know what's the action for it. And then finally, this conformal high spin theory is still quite intriguing, having no conformal anomalies at one loop. So maybe there is more meaning to it also, in spite of being obviously non-unitary in UI. So I don't know how important is that. Thank you.
The loop computations that you didn't show us, they were in flat space or in ADS?
Both. Flat space was once, then it was ADS, and then it was S4 on the sphere. Yeah, in different theories. Yeah.
I think this trick of getting 0 total number to be the freedom for
No, we have fermions. This is also true with if you add fermions, but it's a very special theory. Yeah, it's basically like Chern-Simons theory or n-symmetric tensor theory with whatever rank which is close to dimension. Singlet set, yeah. In curves. Modular invariant. I was discussing 4 dimensions.
Yeah, I know, but there are also analogous constraints in 4 dimensions. You can't just throw away up to 0. Well, in ADS 4 it is. In ADS 4 it is, because you do that to do. In ADS 4 cases. So just asking, is there a consistent way to implement these projections you're making?
Well, one depends. Well, one needs to give definition. If you want to define this theory on any space, yeah. If you just look at this correlation function of currents, that's the answer. Right. Then there is also additional counting of states. It also works. But it's a good question how this singlet, what's the right embedding of this theory with singlet constraint being implemented dynamically. Yeah.